Hello friend, welcome to the abstract algebra class. It is class 21. Here we will solve the problem. Prove that set of four rules of unity form an abelian group with respect to multiplication. Solve the set of four roots of unity is given by g equal to 1 minus 1 I minus I, and multiplication is the operation. We say four roots of unity because we know that here 1 to the power 4 equal to 1 minus 1 to the power 4 equal to 1, I to the power 4 equal to 1, minus I whole power 4 equal to 1. Because of this reason, we say fourth roots of unity. We now solve this problem. The set of fourth root of unity is given by g equal to 1 minus 1 I minus I, and multiplication is the operation. Composition table is in the left side we have multiplication operation, and first row and first column we put the element of set G, 1 minus 1 I minus I, 1 minus 1 I minus I. Now 1 into 1 equal to 1 into minus 1 minus 1 into I equal to I, 1 into minus I minus I, minus 1 into 1 minus 1, minus 1 into minus 1 1, minus 1 into I minus I, minus 1 into minus I, the result will be I into 1 I into minus 1 minus I into I minus 1, I into minus I, it will become 1, minus y into 1 minus I into minus 1 I, minus I into I, it is 1, minus y into minus I, it will be I. Here minus I into 1 minus I into minus 1 I minus 1 I into I 1 minus I into minus I minus 1 minus 1. As we see in the composition table, all the elements formed in the composition table are element of G. Every element which is in composition table, we got it, all of them are in CTG. Therefore it means closure axiom. Actually it is first axiom closure axiom, first axiom closure axiom. The composition table is symmetric with respect to principal diagonal. Here 1 minus 1 and minus 1. Here it is the principal diagonal. According to this principal diagonal, every two elements are symmetric. Minus 1 minus 1 I minus I minus I. Here minus I minus I minus I minus I 1 and 1. Therefore, it is symmetric. It means associative axiom hold. Therefore, second axiom is associative axiom. Associative axiom. Identity element here. One is the identity element. One is the identity element in G with respect to multiplication. With respect to multiplication. Inverse of 1 equal to 1. Inverse of minus 1 equal to minus 1. Inverse of minus 1. Minus 1 into minus 1, it should be identity element. Minus 1 into minus 1, it will be 1. Minus 1 into the inverse of minus 1 is minus 1. The inverse of I. The inverse of I, it should be I into which element should be 1. Here, I into minus I, it is identity element. Therefore, the inverse of I is minus I. The inverse of minus I here I. Minus I inverse equal to I. Therefore, every element of G has an inverse in G. 1 has inverse 1. Minus 1 has inverse minus 1. I has inverse minus I. Minus I inverse has I. Therefore, G with respect to multiplication is a group. For fifth one, commutative axiom. Commutative axiom. The element of corresponding row and column are same. Here, if we see this row, 1, 2, 3, row 3 and column 3, they have same element. See, I minus 1, 1. I minus 1, 1. They have same element. Therefore, it means this composition table satisfies commutative law. Therefore, G with respect to multiplication is an abelian group and order of G is 4. Therefore, G with respect to multiplication is finite abelian group. Prove that CG equal to 1, 2, 3, 4, 5, 6 is a finite abelian group with respect to multiplication modulo 7. Solve. Given that G equal to 1, 2, 3, 4, 5, 6 and multiplication modulo 7 is the operation. First of all, we have to make composition table under the multiplication modulo 7. Here, as you see in the left side, here the operation is multiplication modulo 7. It means if we multiply 1 by 1 or any two elements from column and row, then the remainder will be in this table. Example 1, modulo 1 multiplied by 1 modulo 7 equal to 1. Because 1 into 1 equal to 1, 1 divided by 7, the remainder will be 1. 1 into 2 the product of 1 and 2 will be 2. 2 divided by 7, the remainder will be 2. 1 into 3, 3, 4, 5, and 6. 2 into 1, 2. 2 into 2, 4. 2 into 3, 6. 2 into 4, 8. 2 into multiplication 8, 4 equal to 1, because 2 into 4 equal to 8. 8 divided by 7, the remainder will be 1. Therefore, we have to write 1 here. 2 into 5, 10. 10 divided by 7, remainder will be 3. 2 into 6, 12. 12 divided by 7, the remainder will be 5. 3 into 1, 3. It will be 4, it will be 5 and 6. 3 into 2, 6. 3 into 3, 9. 9 divided by 7, 7. The remainder will be 2. 3 into 4, 12. 12 divided by 7, the remainder will be 5. 3 into 5, 15. 15 divided by 7, the remainder will be 1. 3 into 6, 18. 18 divided by 7, the remainder will be 4. 4 into 1, 4. 4 into 2, 8. 8 divided by 7, remainder will be 1. 4 into 3, 12. 12 divided by 7, the remainder will be 5. 4 into 4 equal to 16. 16 divided by 7, the remainder will be 2. 4 into 5, 20. 20 divided by 7, the remainder will be 6. 4 into 6, 24. 24 divided by 7, the remainder will be 3. 5 into 1, 5. 5 into 2, 10. 10 divided by 7, the remainder will be 3. 5 into 3, the remainder, the product will be 15. 15 divided by 7, remainder will be 1. 5. 5 into 4, 20. 20 divided by 7, the remainder will be 6. 5 into 5, 25. 25 divided by 7, the remainder will be 25. The remainder will be 4. 5 into 6, 30. 30 divided by 7, the remainder will be 2. 6 into 1, 6. 6 into 2, 12. 12 divided by 7, remainder will be 5. 6 into 3, 18. 18 divided by 7, remainder will be 4. 24. 24 divided by 7, remainder will be 3. 30. 30 divided by 7, remainder will be 2. 6. 6 into 6, the 36, the remainder will be 1. So as you see, all elements in this composition table all belongs to G. Actually, the first axiom, closure axiom, hold. That is, all the elements formed in the composition table are element of G. From 1 up to 6 and 1 up to 6, all of them are element of G. It means closure axiom hold. Number 2, the composition table is symmetric with respect to principal diagonal. Here, if we see 2, it is composition table is symmetric with respect to principal diagonal. It means it is the principal diagonal. So if we compare two elements, here 2, also 2, 3, 3, 6, 6, 4, 4, 1, 1, 5, 5, 6, 6. Similarly, 5, 5, 3, 3, 6, 6, 1, 1, 5, 5, 4, 6, 6, 4, 4, 3, 3, 2, 2. It means associative axiom hold in a composition table. identity element. Here the identity element of in this set, and the identity element is 1. 1 is the identity element in G with respect to multiplication, modulo 7. Inverse. Now we want to check the inverse of each element. Here, if we see, according to the definition of inverse element, if two elements which under any binary operation, the result will be identity element is called inverse element. See here, 1 into 1. 1 is 1 in multiplication 1 modulo 7 equal to 1. Therefore, implies 1 is the identity element. Therefore, the inverse of 1 is equal to 1. Now, the inverse of 2. 2 which element the result become 1 identity element. 2 by 4 the element become 1 identity element. Therefore, it means 2 into 4 modulo 7 equal to 1 implies 2 inverse equal to 4. Similarly, 2 inverse equal to 4. 4 inverse equal to 2. 3 here 3 by 5. Therefore, 3 inverse equal to 5. 5 inverse equal to 3. 4 inverse here. 4 inverse we already wrote here. 4 inverse equal to 2. 5 inverse is 3. Therefore, 6 inverse equal to 6. 6 inverse equal to 6. Therefore, for every element of G, there is an inverse in G. Number 5, commutative element. The commutative axiom, the element of corresponding row and column are same. It means here, if we choose any row and same column, they have same element. Example, if we choose second row and second column, they have same element. 2, 4, 6, 1, 3, 5. 2, 4, 6, 1, 3, 5. They are same. Therefore, G with respect to multiplication modulo 7 is an abelian group, and order of G equal to how much? 1, 2, 3, 4, 5, 6. 6. Therefore, G with respect to multiplication modulo 7 is a finite abelian group. Here is 3 more question you have to solve by yourself. I will write here. Number 1, prove that G equal to 1, 2, 3, 4 is an abelian group with respect to multiplication modulo 5. Number 2, prove that G equal to 1, 3, 5, 7 is an abelian group with respect to multiplication modulo 8. Same problem. Number 3, prove that G equal to 1, 5, 7, 11 is an abelian group with respect to multiplication modulo 12. This was the lesson of lecture 21. Thank you.